Now we're going to look at step 4b, in which we compare the p-value with the significance level alpha. Again, the probability value, or p-value, is sometimes denoted by just the letter p. It's just the probability of obtaining a t-test statistic as or more extreme than the one we obtained. So for a two-sided test, right, where the alternative is that the population mean doesn't equal the claimed value, okay, you're pretty much agnostic whether it's going to be above or below. The p-value is just the probability of obtaining a test statistic greater than or equal to, in absolute value, the one we obtained, multiplied by 2. For a right-sided test, the alternative is that the population mean is greater than the claimed value under the null, and the p-value is the probability of obtaining a test statistic greater than or equal to the one we observed. For a left-sided test, where the alternative is that the population mean is less than the claimed value of the null, the p-value is the probability of obtaining a test statistic less than or equal to the one we observed. And again, we compare the probability value, or the p-value, to our level of alpha. So if our p-value is less than or equal to whatever we set alpha to, then we reject the null, and we make a substantive conclusion based on that level of alpha and using that p-value. So let's examine what's going on. Suppose we have a t-test statistic of 2.1. What is our p-value, right? That p-value is going to change depending on the sample size. That's because the shape of the t-distribution changes depending on the sample size. This is why we typically use statistical software to calculate p-values using the t-distribution. But let's look at this. So if our t-test statistic is 2.1 and our sample size is 3, right, then our p-value is about 0.09. That's larger than 0.05. So we would fail to reject the null. That's because that area, all right, in absolute value, all right, more extreme, more positive than 2.1, that area is 0.045. Right? Multiply that by 2, and we have a p-value of 0.09. So the probability of obtaining a test statistic as or more extreme than the one we obtained under a two-sided test, where the alternative is that the population mean doesn't equal the claimed value of the null, that value is 0.09. That's larger than 0.05, so we fail to reject the null. Now, what would happen if we had a sample size of 500, but we had the same test statistic? Right? In this case, right, the probability of obtaining a more extreme test statistic is, in fact, 0.036. Right? This just reflects the fact that with a larger sample size, the t-distribution is more and more like a normal distribution. And so our probability values are going to look more and more like those from a normal distribution. The key point here is that, right, the probability values, they change for a given level of alpha, and for a given level of alpha, and for a given test statistic, depending on the sample size, right, that p-value is going to change. With a smaller sample size, in general, our p-value, using the t-distribution, is going to be larger. For a larger sample size, that p-value will be smaller. This just reflects the fact that we have greater uncertainty inherent in a sampling distribution based on a small sample size. Those sample means are going to bounce around a lot more. All right, so let's look at a few examples using the t-distribution model and calculating p-values.